Okay, video number 3 in the How to Wire Schneider Modicon expansion modules. We're going to be taking a look at TM3 expansion modules, and we're going to look at a very, very special one today that allows us to use 120 volt AC inputs into it. All right, let's define which module that one is. The module itself is going to be the TM3DI, standing for discrete input or digital input, 8, talking about the number of inputs it has, and then A, which is going to be for my AC style. It is the only one in the family. There's no larger ones. You can't get them in, 16s, 32s, or anything like that. 8 is going to be the maximum that we have, and they're really for a very specialized application. We'll take a look at that when we see the drawings later on. Let's go through the data sheet real quick. We see that this thing is going to be usable with all of these families, 241, 251, 221, and 262. The one that is really going to go and excel with is going to be the Modicon 221 because we can get those in 120 volt input, which means that we don't need to deal with an external DC supply, and that's why we like this module in particular. It does have a discrete input voltage of 120 volts, and it has very, very little current that it is going to go and take through those inputs itself. So you can get away with fairly long signaling and instrumentation runs. A bit more detail that is given on these inside of the data sheet deals with particularly the voltage state 1 and the voltage state 0. And what they're talking about over here is where we're guaranteed to go and see a high versus where we're guaranteed to go and see a low. If we look at this one, they guarantee that anything that is going to be 79 volts and above will be a guaranteed high, a digital high, or a one that we would see inside of there. Anything that is going to go and be 20 volts and below is going to be a guaranteed 0 that we are going to have. And anything that is between these two values, 20 and 79, is going to be at what we call an undefined voltage level. Undefined voltage level does not mean that it is not going to trigger as something. It just means that the manufacturer can make 0 guarantees as to what exactly it will trigger as. So if you bring in a voltage right there in the middle, about 50 volts or something like that, that 50 volts could get read high, taking you to a 1, or that 50 volts could get read low, taking you to a 0. So we just don't bring in voltage values that are going to be anywhere near that. It's a nominal 120 volts, keep it at 120 volts, and as long as you have got close to 120 volts or close to 0, it is going to accurately read that as being a high or a low. The input impedance itself is going to be 11K ohm. This goes along with that 7.5 milliamps of current that we saw there before. And it is a slightly slower, compared to some of the others, response time that we are going to see from these ones. Usually just because we're dealing with AC, so we've got a varying waveform, and a varying waveform tends to, wait for more stability before we trigger that thing as being high. But still, 25 milliseconds is pretty quick when it comes to response time. Taking a look at our data sheet shows that we have got two commons. We got an NC, we got a bunch of numbers over here. The first one that I want to go and deal with here is this NC. NC does not mean normally closed. That's oftentimes the way that it is going to be visualized by electricians if they're not familiar with the Schneider branding. They'll assume that this is going to be a normally closed set of contacts in between here. That is wrong. Is not the way this thing is supposed to go and be. NC actually stands for no connection. In other words, we don't take any wire to that terminal over there. All right, so now that that one's defined, we're not going to do anything with it. Let's take a look at the others. For the others here, what we see is that we can go and take one lead of our AC in to our common, and then we can take the other lead of our AC around to the rest of our devices. Now, this being Canada and me being a Canadian, I am only going to go and switch the line. We never switch the neutral, because when you switch the neutral, you could end up with problems out in the field where if you end up with a ground fault and your neutral is grounded, then you can get tracking back. So expressly, we are prohibited from switching the neutral in Canada, which means that for my video over here, I am only going to go and use what we refer to as syncing logic, and syncing logic would be taking my AC common or neutral in over here and taking my AC line out and around to my devices themselves. So we will follow that through on the next sheet. Last thing that before we do that, actually, we'll just talk about the fact that this one also on this data sheet is missing the fusing symbol that we have. We should be taking from our AC supply. We've got an external AC supply. We should be fusing down whatever that lead is going to be so that we are going to have proper protection going into these over here. That fusing is going to be done through the use of usually DIN rail fuse holders. This one here will take class CC fuses, use the fast-acting HCLR type. You can also get the skinny ceramic or glass type like this that are going to go and fit onto your DIN rail as well. Either way, this one or that one, pick something that is going to go and have indicator lights so you can tell when you have got a blown fuse. It just makes your troubleshooting that much faster in the fields. Okay. Here we are at our component that we're going to go and use. And specifically for this one, I picked that we are going to go and use the TM221 CE16R. This is a nice little PLC for doing small scale integration. It gives you a bunch of relay outputs over here, and it has a bunch of 24 volt DC inputs on the top, and it has its own little built-in 24 volt power supply. The problem with this built-in 24 volt power supply is that it's not very large. And so you can go and take care of all your own inputs that you have here, maybe one or two other outputs, but past that, you'd have to go and add in another auxiliary 24 volt supply. And we're trying to get away from that. That's why we're using this 120 volt inputs that we have over here. What we've done is we put this on here. Because of that, you'll note that we don't have a 24 volt DC power supply. Almost every other video or drawing that you're going to see of mine is going to have a 24 volt power supply, but in this case, we can get away from having to buy and install that inside of our cabinet because we're going to go and tap directly off of our line. Okay, the very first thing that we are going to do is we're going to start at our neutral, and we are going to go and take in our reference. We got our commons over there, so we are going to go from my neutral. I'm going to use this light blue for my neutral because drawing with a white marker would be terrible for you all. You wouldn't want to watch those videos, so we'll just draw it in with that light blue like that. We've now got a reference that's being brought in. We see that we're ignoring that NC that we have over there. We now take a positive line. If I follow this through, I got my AC in, I go through a DIN rail breaker, and then I go into these fuse holders here. I've got power all the way up to that point there. So I'm going to take it from this DIN rail fuse holder over here up to my field devices, and I'm just going to go hop, 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 all the way over from screw to screw to screw. Everything now has got a terminal that it's going to be tied to. And now what I can do is I can take each of these back down to their AC inputs over here. Each of them runs down and into their individual inputs. And there we have it. That is going to be our 120 volt input cards. Not the most common of all cards, but really handy when you don't want to have to add in that extra 24 volt power supply. Okay.